common collector configuration of a transistor BJT. We have taken NPN transistor for the characteristic graph of common collector configuration. See, this is our bipolar junction transistor of NPN type. This is emitter terminal, this is base terminal, and this is our collector terminal. Now this arrow is pointing towards emitter from the base, so that's why it's indicating that we have selected NPN type of bipolar junction transistor. Now in common collector configuration, collectors will be common terminal between input and output. So input will be provided between base and collector. The input current is too much small because it is base current, so I have selected a micro emitter to measure this current, and here I have selected milli emitter for this current, and this is our collector. Now VBB is input potential supplied to the base, which is controlled by rheostat R1, and VEE is the input potential to the emitter, which is controlled by R2, and here VEC is the potential between emitter and collector, and VCB is potential between collector and base. This is a common terminal, so that's why it is kept constant. One thing is very important thing to discuss here, why we have always using ground to common terminal. See, it has a very common logic. Suppose you have connected this thing without any ground. In that case, when you are increasing this potential, then this minus effect will come to the collector terminal, and also it will affect to this, because same potential will be carried over a conductive path. So the behavior of output will also be changed. So that's why we have connected it with ground, so it will show a proper behavior. That means there will be no effect of changing this on this potential and changing VE on VB potential. Now in common collector configuration, collector is kept common and input is provided between base and collector, and output is measured between emitter and collector. Now input are base current collector या base voltage characteristic. This is also known as input characteristic. Input characteristics. That's mean input characteristic is the graph between base current plotted between base current and VBC. Collector base voltage VCB is known as input characteristic at constant VCE. That's mean the graph between base current and collector base voltage at constant collector emitter voltage is known as input characteristic graph. So the graph of input will be in this manner. or horizontal terminal will represent VCB, collector base voltage, that will be in bold, and this vertical axis will represent base current, that will be in microampere. Now the graph of current IB will be in this manner. As we will increase our collector base voltage, then it will oppose the flow of current and the current will be downfall. This graph, this first graph is traced at VCB this is at VCE is equal to 2 volt, 2 volt. This is traced at 3 volt and this is at 4 volt, that is VCE, 2 volt, 3 volt and 4 volt. So from this graph we are seeing that as we are increasing our collector base voltage, then current is being reduced. What is there? VCE is equal to VCB plus VEB. That's mean total voltage across collector and emitter will be always equal to voltage across collector and base and plus का emitter and base. तो VCB is equal to VCE minus VEB. Now VEB is equal to VCE minus VCB. From this relation, for a given value of VCE, if VBC will increases, VEB will decreases, and thus the current IB also decreases. Here VEB is equal to VCE minus VCB. In this case, for a given value of VCE at a constant value of VCE, if we are increasing VBC, then VEB will be decreases, and so that's why it will affect the base current. So IB will decreases. Then the graph is always in such manner that the current is being decreased. Here VCB. Now output characteristic. Output characteristic of common collector configuration. In case of output characteristic, we will plot the graph of IE, that's mean graph between IE and VCE at constant base current is known as output characteristic for common collector configuration. Now we will keep our input potential VCE at horizontal axis and current IE at vertical axis. So this is our current IE. IE will be in milliampere and here VCE is in bold and IB should be constant. Now we know that IE equal to IC plus IB. In that case, in increment of the IB, IE is equal to IC plus IB. So due to increase in IB, IC will increase and IE is also increases. So that's why the graph will be in this manner. If the value of IB should be constant, then I am plotting the graph for different value of base current. Suppose here IB is equal to 20 milliampere, 20 microampere. Then I have increased IB to 30 milliampere, sorry 30 microampere, and here IB is equal to 40 microampere. So from this graph we are seeing that current IE is increases with the increase in IB and also with the increase in collector emitter voltage. VCE is plotted. The experiment can be repeated for different value of IB, so the current will be higher. Now for a given value of base current IB, IE first increases rapidly. For a particular current, suppose we are considering the graph at 20 microampere, then in that case we are observing that for this given value the graph is being increased rapidly from this region to this region, and after then its increment became very slow. That's mean increase in emitter current is became slowly than earlier. Now when we are considering 30 microampere base current, in that case at 0 VCE IE is 0 milliampere, and when we are increasing IE, then graph increases rapidly, and after a particular region we are observing that the graph increases very slow. So that's why for a given value of base current, the graph for emitter current increases rapidly, and after a particular value the increase in emitter current with the increment in the collector emitter voltage become slow. Second point, for a given value of VCE, the emitter current IE increases with the base current. That means there is a particular value VCE, there is increase in the emitter current with the increase in base current. See here, if we are seeing 2 volt potential of VCE, in that case here the current is of let 2 milliampere, here is 3 milliampere, and here is 4 milliampere. In that case at 20 microampere the current is 2 milliampere, while at 30 microampere the current is 3 milliampere, and at 40 microampere of base current the current is 4 milliampere. So with the increase in the base current, the emitter current is also increases. common collector configuration. So that's why common collector configuration is also known as emitter follower circuit. Emitter follower circuit. This circuit will be discussed later, because why we know this common collector configuration as a collector for as emitter follower circuit, then we will discuss in our next lecture. Now we have to discuss now current gain in common collector configuration and its relation with the alpha and beta. In our both previous configuration, common base and common emitter, we have founded the gain, current gain, alpha and beta, and now we are going to find the relation between emitter current and base current and the current, and that is the current gain in common collector configuration. So current gain in common collector configuration is similar, the ratio between output current and input current. Here it is denoted with the help of gamma, that is equal to output current, that is IE, upon input current, that is base current, at constant collector emitter potential. When we are considering gamma DC, then it is IE upon IB. When we are considering gamma AC, in that case gamma AC will be equal to change in emitter current upon change in base current with constant collector emitter change. Now we need to find the relation between del IE and del IB, that's when gamma AC between alpha and beta. So first of all, relation between gamma and alpha. We know that IE is equal to IC plus IB. Similarly, IB can be written as IE minus IC, and gamma is equal to IE upon IB. So gamma is equal to IE upon IE minus IC. So gamma is equal to IE upon IE can be written as 1 divided by IE upon IE 1 minus IC upon IE, that is known as alpha. So gamma is equal to 1 upon 1 minus alpha. This is the relation between alpha and gamma, and gamma AC is equal to 1 upon 1 minus alpha AC, and similarly gamma DC is equal to 1 upon 1 minus alpha DC. Next, relation between gamma and alpha. relation between gamma and alpha. Now, we can replace the value of IE in the term of IC and IB, then it can be written as gamma is equal to IE upon IB. So gamma is equal to IC plus IB upon IB. Now divide this term, gamma is equal to beta plus 1, beta plus 1, or gamma is equal to 1 plus beta. This is relation between gamma and beta. When we are considering gamma AC, then gamma AC is equal to 1 plus beta AC, and gamma DC is equal to 1 plus beta DC. This is the relation between gamma and alpha, and this is relation between gamma and beta. In case of common collector circuit, the input resistance is very high. Now we need to find the relation between input resistance. So input resistance R input is equal to VCB, collector base voltage, upon IB. See, VCB is collector base voltage, that, and collector base is always collector base junction is always reverse bias. So resistance will be high. In both previous configuration, we have provided input between collector and base. Current of input in common base was base current, and in common emitter, that was base current input, and common base configuration emitter current was input used as input. But here the common collector configuration, collector base junction is always reverse bias. So that's why similarly, when there is reverse bias PN junction diode, then there will be higher value of resistance, and also IB is in microampere, while VCB is in volt. Then R input is high. R input is high. When the output resistance, when we are considering output resistance, then R output is low. The voltage gain in this case is less than 1, because V output upon V input is equal to IE into R output upon IB into R input. IE upon IB is equal to gamma, that multiplied with R output upon R input, that is less than 1, and this is equal to 1 plus beta time multiplied with less than one quantity. So voltage gain, G is used to represent gain and V for voltage gain is less than 1. Due to this reason, the circuit is not used for amplification. When voltage gain is less than 1, it is not used. It is not used as amplifier. This circuit is however generally used in impedance matching. We can use it as a impedance matcher. Impedance matching. Thank you.